So far, I've defined sets to be a bunch of objects, and that's a very vague and slightly sometimes useless definition. But we did also have two extra conditions put on it to make it a little more precise. The two conditions were that each element of a set occurs only once. If it occurs more, then you have what's called a multiset, but here we only have sets, so each element occurs only once. And we also had that there's no necessary conditions on the elements that might relate them to each other. So they're not, for instance, ordered. If you do have an ordering of the elements in a set, then you've got what's called an ordered set, and we'll look at that actually soon. But so far we've looked at these particular conditions on a bunch of objects. Now, of course, that's not a very precise definition, and if you did want to make it more precise, then you might go to some trouble, and that might be worth it because, well, if you want to rely on mathematics, then you might want to see that your foundation is solid, that you can build your grand edifice of mathematical knowledge and results and on a foundation that you can actually trust. And that's what Whitehead and Russell did a century ago, roughly a little over a century ago. This is the Principia Mathematica, a famous work, and this version here is roughly half a century old. It's from 1962, which was roughly 50 years after the first version, but it's basically the same book as what they wrote, and there are, of course, newer reprints of this as well. So what they wanted to do was build this solid foundation of mathematics, and it turned out famously that this is actually not possible, as Gödel later showed. You can't actually build any foundation that will hold all of the types of mathematics that we might invent or discover or whatever. But it's still a very impressive work, and they did a massively thorough job. Now, if you look at it, you might not be able to immediately read it. Like, you've got pages like this where it just looks like squiggle. Are they making it up? Is this actually mathematics? But yeah, they go very, very thoroughly about it. So near the end of the book, they even get to the point where, on page 360 in this version, that they prove that 1 + 1 is 2. So yay, now we have numbers. We even have addition of 1 and 1. So that's how thorough they went, and that is pretty cool. Now, yeah, the background to this is that technology and science and mathematics was in glorious ascent during the 19th century, and people were getting quite optimistic that now we pretty much know everything about nature and physical laws, and even psychology was coming up, and mathematics was booming, and technology was transforming lives and culture. And there was this optimistic sense that science and would enrich culture, make us civilized and happy and healthy, and so you want to just fill in the details. You want to figure out everything in science, but you've already found the natural laws. We've found basically most of mathematics now, and we just have to sort of write it down, and that's what they thought. And of course, then that cultural optimism, which is called positivism back then, of course, suffered a big blow, not only with Gödel's discoveries in the early 30s, but also that you had the Great War, the First War, which was this monumental tragedy and atrocity that was largely helped by technology. The savior of society and mankind was now to blame for this atrocity, and that put a dent in the optimism. And also then you had Einstein and others coming to show that the laws of nature were not at all discovered. The world is much crazier, much more unreal and putative, and reality, what is that? And then philosophical questions were asked, and in mathematics there were upheavals as well, as you can see, and so on and so forth. And so it's a dangerous thing to be a little bit too smug and optimistic that you found all the solutions. So One thing that led to the Principia Mathematica were it came out of some philosophical thoughts about paradoxes from Frege and also Wittgenstein. And Russell was talking with these philosophers, and a very philosophical person himself, and also Bertrand Russell, the other author, a very important philosopher as well. But there was this one paradox which shows you why you have to be a little bit careful when you're defining what a set is. So if we define S to be the set of all sets, why not? A bunch of stuff, the stuff is now sets, for which this set here, we could say A is a set, just to make sure what we're talking about, and, this is a little and sign, A is not contained in itself. Okay, we can write that down. Now we've written it down, that's fine. But now the question comes, and this is Russell's paradox. And I'll just, yes, there were two L's there, great. The paradox is this: is S in that set? Well, S is a set. We've drawn the curly brackets, so you know it's a set, we claim. But is it contained in itself? Well, if it's not contained in itself, then it satisfies the conditions here, and therefore it's contained in itself. But then it's not satisfying this condition, so it can't be contained in itself. Oh, but I'm confused now. Are you in the set or aren't you? You know, are you in your own set or aren't you? And neither makes sense. So this is a paradox. In general, and you might want to think of what's going wrong, and you know, have we destroyed mathematics? You know, that would be a pity. You know, it's I like mathematics. I don't want to destroy it, but no. The thing here that's going wrong is that we have self-referencing going on. So if you have self-referencing, then like the Ouroboros eating its own tail, it sometimes leads to paradoxes. So if you want to define things in a well way, then you could avoid self-reference or be very careful with it. In this case, you'd not be sufficiently careful. So if we have a more sort of linguistic approach, then you could have this sort of simple self-reference, like this sentence here. This sentence is a lie. Okay. If it's a lie, then it's true, but then it's not a lie, but then it's true, and so forth and so on. So that's the self-referencing. This sentence refers to itself. And you can find many more things. If you want to avoid these sort of paradoxes, then you could say, in here, for instance, all these sets except S, and then you get out of it. And the course notes give a few more details and another analogy of this sort of situation.